Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at one-dimensional invariant subspaces and specifically eigenvalues and eigenvectors. So in this topic we will define invariant subspaces, we will define eigenvalues and eigenvectors, we will consider some consequences and theorems that derive from our definitions, and then we will determine how to find eigenvalues and how to find eigenvectors and look at numerous examples. Now, suppose that we have a linear operator A mapping U to itself, and it has the property that it maps a particular vector onto a scalar multiple of itself. That is, there is a non-zero vector U such that A times U is equal to some scalar multiple lambda times U. Now, we will always exclude the zero vector from being such a candidate, as alpha times 0 is equal to lambda times 0 for all scalars. So there's no significant information gained from that. Now, if there exists such a vector U, that vector is said to be an eigenvector of A, and the corresponding scalar multiple lambda is the eigenvalue associated with the eigenvector U. Now, if an n by n matrix has n eigenvalues counting multiplicity, then the eigenvectors and their corresponding eigenvalues completely describe the behavior of the matrix. That's what we're going to be focusing on. Unfortunately, a real square matrix that has an odd dimension is actually only guaranteed to have at least one real eigenvalue and a corresponding eigenvector. And a real square matrix that does not have at least one real eigenvalue must have at least one complex conjugate pairs of eigenvalues if you are thinking about it in the complex plane. And what this actually describes is a two-dimensional invariant map. What does that mean? Well, here is a rotation matrix that rotates R2 by 90 degrees. So no vector is left unchanged. Actually, it rotates it by 90 degrees and expands it by root 2. We will focus on finding conditions under which the eigenvectors and corresponding eigenvalues fully describe the behavior of the linear operator. And we will see that this happens when the matrix is symmetric. Now, for example, consider a real matrix D that is a diagonal n by n matrix, and E sub k is the kth canonical basis vector in R to the n. In this case, the diagonal matrix times the kth canonical basis vector is simply going to be that kth diagonal entry times that canonical basis vector. And so for a diagonal matrix, each canonical vector E sub k is an eigenvector with a corresponding eigenvalue equal to the kth entry on the diagonal. For example, if this is our diagonal matrix, note that if we were to multiply the basis vector 1, 0, 0, 0 by this matrix, then you get -3 times that vector. So the eigenvector is the first canonical basis vector, and the eigenvalue for this particular matrix is -3 for that eigenvector. So our first canonical basis vector has an eigenvalue of -3. Our second canonical basis vector has an eigenvalue of 2. The third has an eigenvalue of negative 0.1, and the fourth canonical basis vector has an eigenvalue of 0.5. Now, if a linear operator A has a non-trivial null space, then for each vector u in that null space, it has the property that A times u is equal to the 0 vector, which is equal to 0 times u. That is, for each vector in the null space, it is an eigenvector with a corresponding eigenvalue of lambda is equal to 0. Now, the null space is all eigenvectors that have an eigenvalue of lambda equals 0. Now let lambda possibly be non-zero. Let us consider all eigenvectors that have that same eigenvalue. Theorem. Given a linear operator A, the collection of all eigenvectors for a given eigenvalue lambda forms a subspace. Proof. If u1 and u2 are eigenvectors corresponding to an eigenvalue lambda, well, then it follows that A applied to u1 is that scalar multiple of u1, and A applied to u2 is that same scalar multiple of u2. So now let us apply A to a linear combination of the vectors u1 and u2. Well, by linearity, we can see that the operator applied to the linear combination is that same linear combination of the operator applied to each of the vectors. But those vectors are eigenvectors, and therefore the first is lambda times u1 and the second is lambda times u2. Well, we can factor out a common term of lambda. And so now we see, oh, wait a second, A times that linear combination of vectors is equal to lambda times that same linear combination of vectors. Thus, alpha u1 plus beta u2 is also an eigenvector with eigenvalue lambda. Thus, every eigenvalue is associated with an eigenspace of eigenvectors, this eigenspace being a subspace of the vector space that the linear operator is acting upon. Because it is a subspace, however, we can also find a basis for that subspace. And where possible, we will actually prefer that basis to be orthonormal, that is, mutually orthogonal and normalized. Now, another theorem. Suppose that a linear operator A has m eigenvalues lambda 1 through lambda m, and that there are m eigenvectors u1 through um corresponding to each of these eigenvalues respectively. So therefore A applied to u5 is equal to lambda 5 times u5. Then, if this is the case, if all of the lambda sub k's are distinct, then the vectors are guaranteed to be linearly independent. All right, before we go through the detailed proof, recall that if a collection of vectors is linearly dependent, then there is a first vector u sub L that must linearly depend on the L-1 vectors that precede it, where all L-1 previous vectors are also linearly independent. We will then proceed as follows. We will assume the converse to what the theorem states, that is, eigenvectors corresponding to different eigenvalues are nevertheless linearly dependent. If this is the case, then there must be a first eigenvector that linearly depends on the previous L-1 linearly independent vectors. However, we will see that this leads to a contradiction, as this will show that the previous L-1 vectors must also be linearly dependent. A contradiction. Recall that m vectors being linearly independent is equivalent to saying that the only solution to a linear combination of those vectors equaling the target vector 0 is the trivial solution when all of the coefficients are 0. All right, so on to our theorem. Again, suppose a linear operator A has m distinct eigenvalues lambda 1 through lambda m, and there are m eigenvectors u1 through um corresponding to these eigenvalues respectively. Then the vectors are linearly independent. Proof. Assume that these vectors are linearly dependent, in which case there must be a first vector in that list, u sub L, that linearly depends on the previous L-1 linearly independent vectors. So therefore u sub L is equal to a linear combination of the previous L-1 vectors where not all alpha sub k are 0. Now, first, we note that u sub L is nevertheless an eigenvector, and thus A multiplied by u sub L is equal to lambda sub L u sub L. Consequently, A multiplied by u sub L is equal to lambda sub L times the linear combination of the first lambda L-1 vectors that equals u sub L. And so distributing the scalar multiplication across the vector sum, we have the following. However, A is also linear, and therefore A times u sub L is equal to A multiplied by this linear combination. But the linear combination, the linear operator applied to a linear combination is that same linear combination of that operator applied to the individual vectors. But all of the first L-1 vectors are eigenvectors. Consequently, each one of them is equal to some scalar multiple times itself when that eigenvector is multiplied by A. All right, so now we have two items or two linear combinations that are equal to each other, so we will equate them. So given this linear combination, two linear combinations that equal each other, let us bring all of the terms to one side and factor out the common alpha sub I, u sub I terms. So now we have lambda sub L minus lambda sub 1, and lambda sub L minus lambda sub 2, and so on and so forth. Now, we assumed that all of the eigenvalues were different. So every difference of two different eigenvalues must be a non-zero value. So on top of that, when we found the linear combination of the first L-1 vectors that equaled the Lth vector, we assumed that not all of the alpha sub k's were 0. Consequently, we now have those same alpha sub k's multiplied by a non-zero value. Basically, what we now have is we have a linear combinations of the vectors from 1 to L-1, which equals the 0 vector, but not all coefficients of which are 0. Therefore, the first L-1 vectors are linearly dependent, which contradicts our assumption that U sub L was the first linearly dependent vector that depended on the previous ones. Therefore, contradiction, and therefore our original hypothesis is correct. Eigenvectors corresponding to different eigenvalues are linearly independent. As a consequence, a linear operator mapping a vector space to itself cannot have more than n distinct eigenvalues. Now, here's a useful theorem that you will need in your quantum mechanics course. If A is a self-adjoint linear operator, its eigenvalues are real. Proof. Well, first of all, taking the inner product of U and A times U, that is equal to the inner product of U and lambda times U, and the scalar multiple can come out of the inner product. But, on the other hand, the inner product of U and A times U is equal to the adjoint of A multiplied by U inner producted with U. But A is self-adjoint. Consequently, this is equal to A times U inner producted with U. But A times U is equal to lambda times U, and because the inner product is sesquilinear, if the scalar multiple comes out of the first term, we must take the complex conjugate. Consequently, notice that two items are equal, but lambda equals the complex conjugate of lambda. Therefore, lambda must be real. Here's another nice theorem. If A is a self-adjoint linear operator, eigenvectors corresponding to different eigenvalues are orthogonal. Proof. Well, suppose that we have two different eigenvectors, U sub 1 and U sub 2. Now, the inner product of U sub 1 and A applied to U sub 1 is equal to U sub 1 inner producted with lambda 2 times U sub 2, and that lambda 2 can come out of the inner product. On the other hand, the inner product of U sub 1 and A times U sub 2 is also equal to the adjoint of A applied to U sub 1 inner producted with U sub 2. But the operator A is self-adjoint, and consequently that is equal to the A times U sub 1 inner producted with U sub 2. And because U sub 1 is an eigenvector, therefore that equals lambda 1 times U sub 1 inner producted with U sub 2. However, notice that in the previous theorem, we showed that all eigenvalues are real, and therefore we can take out lambda sub 1. All right, having done so, we have now shown that two items are equal, and yet we have A times B and C times B, where A and C are not equal. Therefore, the only way that this can be equal is if the B term is 0. Consequently, the inner product of U1 and U2 must be 0, and therefore they are orthogonal. So that is the only possible conclusion we can draw, and therefore two eigenvectors from two different eigenvalues for a self-adjoint linear operator must be orthogonal. Now, let a linear operator A map a field to the n to that field to the n. That operator is invertible if and only if it has no zero eigenvalues. Proof. Assume A is invertible. In this case, the null space is just the zero vector. Thus, no non-zero vector maps to the zero vector, and thus there is no vector with a property that A applied to U is equal to the zero vector, which is equal to 0 times U. So no vector is an eigenvector with the eigenvalue 0. On the other hand, assume A is not invertible. In this case, the null space has at least one non-zero vector in it, U. Thus, A applied to U is equal to the zero vector, which is equal to 0 times U, and thus A has a 0 eigenvalue. Our next goal will be to find eigenvalues of a matrix. So, in order to find the eigenvalues of a matrix, we must first recall that a linear operator A mapping f to the n to f to the n is invertible if and only if the determinant is non-zero. Conversely, this is equivalent to saying a linear operator is non-invertible if and only if the determinant is 0. Also recall that a linear operator is invertible if and only if the null space is just the zero vector. And equivalent, a linear operator is non-invertible if and only if the null space has dimension at least 1. Finally, we saw that a linear operator is invertible if and only if that operator has no zero eigenvalues. The converse to this, of course, is that a linear operator is non-invertible if and only if the operator has at least one zero eigenvalue. Now, suppose we want to find values of lambda such that A times U is equal to lambda times U. This is equivalent to saying lambda times U minus A applied to U is equal to the zero vector. Now, lambda is a scalar, A is an operator, so we can't do anything with that combination. However, recall that the identity operator times U is equal to U, and so we can substitute U with the identity operator times U into the equation. So now we have lambda times the identity operator all applied to the vector U. So this is now essentially of the form B applied to U minus A applied to U, where B and A are linear operators, and that is equal to B minus A all applied to U. So in this case in particular, we have lambda times the identity operator minus the operator A, all applied to U, is equal to the 0 vector. But lambda times the identity minus A is a linear operator. So for this to be possible, the null space of lambda times I minus A must have dimension greater than or equal to 1. Therefore, we must find lambda times the identity operator minus A such that that operator is not invertible. Now, how do we know if something is not invertible? We know that lambda times the identity operator minus A is not invertible if the determinant is equal to 0. Now we will see soon that the formula, the determinant of lambda times I minus our linear operator A, is actually a polynomial in lambda of degree n. It will therefore have n complex roots counting multiplicity. If the matrix A itself is real, then the coefficients of this polynomial will also be real, and therefore the n roots will be either real or come in complex conjugate pairs. Now, this polynomial is called the characteristic polynomial of the linear operator A. Let's try this out. Here we have the matrix A1 equaling 2, 3, 0, 4. Thus, lambda times I minus this matrix is simply the matrix lambda minus 2, negative 3, 0, lambda minus 4. And therefore, the determinant of this matrix is the product of the diagonals minus the product of the off diagonals. Well, the off diagonals is 0, so we are simply left with lambda minus 2 times lambda minus 4. Well, the roots of this particular polynomial are lambda equals 2 and lambda equals 4. So these are our two eigenvalues. Let's try it again with a different matrix. 2, 3, 1, 4 now. So once again, lambda times the identity operator, or the identity matrix, minus this matrix is simply the matrix lambda minus 2, negative 3, negative 1, and lambda minus 4. Taking the determinant of this, we simply get lambda minus 2 times lambda minus 4 minus negative 3 times negative 1. Expanding this, we have lambda squared minus 6 lambda plus 8 minus 3, and that simplifies to lambda squared minus 6 lambda plus 5, and therefore the two eigenvalues of this second matrix are lambda 1 equals 1 and lambda 2 is equal to 5. Of course, what that says is that this matrix also is invertible. Here's a third example. This is a symmetric matrix. Now, lambda times the identity minus this matrix gives us this matrix here. Lambda minus 2, negative 3, negative 3, lambda minus 2. The determinant of this matrix is just lambda minus 2 squared minus negative 3 squared, which expanded is lambda squared minus 4 lambda plus 4 minus 9, which is equal to lambda squared minus 4 lambda minus 5, and you should be able to deduce that the roots of this polynomial are negative 1 and 5. So thus we have our two roots. Here's another example. Now here, lambda I minus this matrix gives us this matrix here, and we calculate the determinant of this matrix. So If we expand this, we get this quadratic, which simplifies to this. And if you calculate the discriminant, you will see that the discriminant is negative, and consequently, this quadratic has two complex conjugate pair roots. Specifically, those two roots are shown here, which equals 4 plus or minus root negative 36 all over 2, which simplifies to 2 plus or minus 3j. So these aren't really eigenvalues because there is no real vector such that when I multiply that real vector by this matrix, I get that vector there, or I get that scalar multiple there. However, if I was to interpret this matrix as a mapping from C2 to C2, then yes, indeed, I could state that 2 plus or minus 3j are two eigenvalues. In either case, of course, this is an invertible matrix. Now, let's find the eigenvalues of this 3 by 3 matrix. This is the most you will ever have to do in this course. Now, lambda times the 3 by 3 identity matrix minus this matrix gives us this matrix here. Now, you will recall calculating the determinant of a 3 by 3 matrix may be done as follows. Duplicate the matrix, then multiply these three entries and add to that the product of these three entries and add to that the product of these three entries. Then subtract from that the product of these three entries and subtract the product of these three entries and finally subtract the product of these three entries. That is the determinant of a 3 by 3 matrix. Consequently, the determinant of this matrix can be written as follows. Now, please remember, this trick does not work for 4 by 4 matrices. It does not generalize. However, given this matrix here, we can expand out the various terms and then collect. And if you were astute or used the appropriate symbolic computation software, you would find that this can be factored as follows, and consequently, the eigenvalues of the above matrix are lambda 1 is equal to negative 3, lambda 2 is equal to 2, and lambda 3 is equal to 8. Now, you will notice that I always write the eigenvalues from smallest or most negative to most positive. You don't have to do this, but when you are calculating the eigenvectors, make sure you keep track of which eigenvector corresponds with which eigenvalue. Let's do this again with this 3 by 3 matrix. Again, lambda times the 3 by 3 identity matrix minus this matrix gives us the matrix we see here, and taking the determinant of this, we get this large unwieldy expression. However, we can expand and collect, and well, we just noticed that 0 is one of the roots of this particular polynomial, and so this is our factored expression, and therefore the roots are 0, 3, and negative 4. So our three eigenvalues are lambda 1 is equal to negative 4, lambda 2 is equal to 0, and lambda 3 is equal to 3. Taking a look at the original matrix, we now know that this is not invertible. So consequently, what this means is, as no one column vector is a scalar multiple of another, this must mean that every single column can be written as a linear combination of the other two columns. Justify that to yourself for a sec. All right, and so this matrix is not invertible. Here's another example. Again, here's lambda times the identity minus this matrix. Taking the determinant of it gives us this expression here. We can expand it, collect, and now we notice that we can factor out a lambda minus 9. However, the discriminant of the remaining quadratic is negative, and consequently the other two roots of this characteristic polynomial are complex conjugate pairs. So for this matrix, there is only one real eigenvector and one real eigenvalue and one eigenvector that, when multiplied by this eigenvalue by this matrix, will result in that eigenvector being stretched by a factor of 9. Now, suppose we have an eigenvalue lambda such that we know that A applied to u is equal to lambda times u for some unknown at this point eigenvector u. How do we find this particular eigenvector u? Well, how about solving the homogeneous system of linear equations given by this expression? Therefore, given an explicit value of lambda, we will place this value into the system of homogeneous linear equations, and we will then find a basis for the null space of this specific system of linear equations. Now, the number of linearly independent eigenvectors for a given eigenvalue will be at least 1, since it's not invertible, so the null space must have dimension at least 1, but it is also not going to exceed the multiplicity of the eigenvalue. And we'll see some examples of all of these. Now, recall that our first matrix had the eigenvalues 2 and 4. To find the corresponding eigenvectors, we will substitute both 2 and 4 into this homogeneous system of linear equations. So, starting with lambda 1 is equal to 2, substituting 2 in, we notice immediately that the first column is equal to 0, and therefore we can easily eliminate the negative 2 in the second row by adding an appropriate scalar multiple of the first row to that one, and we are left with the matrix 0, -3, 0, 0, which is, of course, in row echelon form. Therefore, this says that alpha 1 is free and -3 times alpha 2 is equal to 0, so therefore alpha 2 is equal to 0. Thus, our eigenvectors corresponding to the eigenvalue 2 are all scalar multiples of the vector 1, 0. And indeed, if you multiply the vector 1, 0 by the matrix A1 on the left, you get the vector 2, 0, which is exactly twice the vector 1, 0. Next, if we substitute into that homogeneous system of linear equations the value lambda 2 is equal to 4, we get the following system, which, is already in row echelon form after that subtraction is made in the second row. So there's nothing to do. Alpha 2 is a free variable, and we can determine that alpha 1 is equal to 0.5 or 1.5 times alpha 2. Therefore, our eigenvectors corresponding to the eigenvalue 4 are all scalar multiples of this particular vector. So for example, if we multiply that vector by 2, we get the vector 3, 2. And if we multiply the matrix by 3, 2, we get, oh, what do we get? Yes, we do. We get 12, 8, which is 4 times the vector 3, 2. Here's our second matrix, and you'll recall that it had eigenvalues 1 and 5. Thus, given the homogeneous system of linear equations, we will substitute in lambda equals 1 and lambda equals 5 and solve to find a basis for the null space, which will therefore give us the eigenvectors corresponding to each of these eigenvalues. So for lambda equals 1, substituting that in gives us the matrix -1, -3, 0, and that repeated. So we just have to add -1 times row 1 onto row 2 to bring it into row echelon form. And therefore we see that alpha 2 is free and alpha 1 is equal to -3 times alpha 2. So consequently, our eigenvector is -3, 1. And if we were to multiply -3, 1 by that matrix, we get -3, 1, which is exactly what we were anticipating, because the eigenvalue is indeed 1. Now, if we substitute in the value lambda equals 5, then again, solving that gives us that equation here. So once again, that row echelon form matrix there, which tells us that alpha 2 is a free variable and alpha 1 is equal to alpha 2. Consequently, the eigenvectors of lambda equals 5 as an eigenvalue are all scalar multiples of the vector 1, 1. And once again, if we multiply the matrix A2 by the vector 1, 1, we do get the vector 5, 5, which is 5 times longer. Here we had a matrix that had a 0 eigenvalue and the other eigenvalue was 7. Once again, we will substitute in both values of lambda into this homogeneous system of linear equations. And therefore, substituting in the value 0 gives us this matrix here, and applying Gaussian elimination very quickly demonstrates that alpha 2 is a free variable and alpha 1 is equal to half of alpha 2. So consequently, the vectors that are a scalar multiple of 0.51 are all eigenvectors with the corresponding to the eigenvalue 0. Thus, this includes all vectors in the null space. So, for example, if you were to multiply the matrix above by the vector 1, 2, you would see that that does indeed equal the vector 0, 0. Substituting in lambda equals 7 gives us a different system augmented matrix, and once again applying Gaussian elimination gives us this matrix here, and therefore once again alpha 2 is free and alpha 1 is equal to -3 times alpha 2. So therefore all scalar multiples of -3, 1 are eigenvectors for the eigenvalue 7. And once again, if you were to multiply the two vectors together, you would get -18 minus 3, which is -21, so 7 times larger for the first one, and +6 plus 1, 7, which is once again 7 times larger than 1. Recall that the matrix B1 had eigenvalues -3, 2, and 8. Now what we will do is we will substitute these 3 eigenvalues into the matrix lambda times the identity minus this matrix B1. And we're not going to bother with the augmented matrix because we're solving the homogeneous system anyway. So keeping that in mind, when lambda 1 is equal to -3 is substituted into that matrix, we get the matrix that we see there, -5, -2, -10, -2, -7, -4, -2, -1, -4. And if we add appropriate multiples of row 1 onto rows 2 and 3, we get zeros in the interesting locations. And then we just have to add an appropriate multiple of row 2 onto row 3, which is going to eliminate that term anyway. So now we see here that alpha 3 is free, alpha 2 is equal to 0, and alpha 1 is equal to -2 times alpha 3. So our first eigenvector is -2, 0, 1. And if we multiply the matrix by that vector, we get the vector 6, 0, -3, which is, of course, the that vector times the eigenvalue -3. For lambda equals 2, substituting it into the matrix, once again, now we actually have to do a row swap to bring a non-zero term into that top left-hand corner. And then we'll add an appropriate multiple of that row onto row 3 to zero out the first column. We can add half of row 2 onto row 3 to eliminate those entries. And once again, we see that, oh, this time alpha 3 is free. Alpha 2 is equal to -5 times alpha 3, and we can solve for alpha 1 as well, which is 3 times alpha 3, and thus the solutions are, therefore the eigenvector is 3, -5, 1, and if we multiply 3, -5, 1, for example, you get, first you get 6, -10 plus 10, which is 6, which is indeed twice 3. 6, -20 plus 4, which is equal to 10, which is -10, which is once again twice -5. And in the last location, we would get 2, which is of course twice 1. Now, for the last eigenvalue, we substitute in 8. And now we have a few fractions in there, but that's not significant. When we do solve for the basis vector of the null space of that particular matrix, we get that the eigenvector is consequently 2.4, 2.2, 1, and all scalar multiples thereof. And if you were to try it out, you would actually see that yes, indeed, multiplying that vector by that matrix does give you a vector that is 8 times that longer. Following this topic, you now understand the definition of an eigenvalue and an eigenvector. You know that eigenvectors corresponding to different eigenvalues are linearly independent. You know that the eigenvalues of a self-adjoint operator are real and that the eigenvectors corresponding to different eigenvalues of such an operator are orthogonal. You know how to find eigenvalues and you know how to find eigenvectors. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!